for the invitation. And this is my second talk for the Sigma Club. The first was more than 30 years ago, when it was still chaired by Michael Redhead, who was also the founder. It was in Cambridge at the time. And then the format was actually 2.5 hours, so there was a 1 hour talk. Then there was a 1 hour summary by Redhead, which was basically a new version of the talk on a similar topic. Hi. And then there was Q&A, so you've omitted the Redhead summary, and otherwise everything has stayed the same. I'm not a philosopher, I'm actually a mathematical physicist, and I counted that I'm in the 25th year of my professorship, and I thought it became time to figure out what was actually going on in this field. But as some of you know, I like to hang out with philosophers. In fact, that's how I got to know Michael Redhead and the likes. Let's see. The picture you will be able to reinterpret when the talk is over. Right, so also in the abstract that I posted, I started with a quote that I will repeat. It's by Mark Steiner, who was really a philosopher of applied mathematics and mathematical physics. And it says, to an unappreciated degree, the history of Western philosophy is the history of attempts. What's this moving insect? Or
yeah, it's this.
It's an actual insect.
Oh, there's another one.
I thought it was the castle.
It's an interesting distraction. Okay, so to an unappreciated degree, the history of Western philosophy is the history of attempts to understand why mathematics is applicable to nature, despite apparently good reasons to believe that it should not be. And then he mentions just the ultimate canon of male, I should say, philosophers that actually spent considerable time and energy on this problem of applicability of mathematics and failed to solve this, I think. But that was still, in a way, an easy version of the problem compared to the philosophy of mathematical physics, because all their efforts, or most of them at least, was about elementary mathematics that actually originated in applied mathematics. So you certainly know that geometry and arithmetic originated in the application to length measurements, taxation, accountancy, and so on. And so even for mathematics that comes from application, it was difficult to understand why it's applicable and how it can be applicable. And if you move towards physics slowly, so Galileo's famous words that the book of nature, the grand book, the universe, is written in the language of triangles and circles and other geometric figures, it's still about that kind of mathematics that's supposed to be all around us. And so even that problem is very difficult. And it's nothing compared to the problem of mathematical physics. And so in that simple setting, the original good reason why people believe that it's actually impossible that mathematics is applicable was, I would say, Plato's insistence that, for example, the irrationality of the square root of 2 cannot be empirically verified. And that seems to sort of cut the problem into 2 halves. There's this theorem about the irrationality in the square root of 2, and there's an actual triangle supposed to have that diagonal where you simply cannot see this or measure it. And more generally, I would say the Plato, and I think many people still believe that there's certain timelessness and certainty and immortality in mathematical theorems that you don't see in empirical reality, which is sort of problematic. It's uncertain and it changes. Okay. However, the problem of mathematical physics is more difficult, I believe, and I attribute this to Newton's introduction to the gravitational force. I guess you're all aware that the work of Newton was a turning point in every conceivable way in the history of science, but also here, since he explicitly introduced the gravitational force as a mathematical construction, and then it's really different from a circle. A circle may be a planetary orbit, and you can say, well, it's there. But the formula for the gravitational force, you can't really point to it. It's unclear. And I think this went on, this became the dominant trend in mathematical physics. So mathematical physics after Newton developed in a way that it sort of introduced mathematical constructions which you cannot reasonably maintain that it's in nature or around us, or we can point to it. And so I would say there's a continuous trend to the 20th century. I'll give two lines of development that illustrate this, both starting with Newton. So if you say the gravitational force was sort of abstracted into the concept of a potential by the French, and one way of thinking as the metric in general relativity is just, it's a matrix of 10 gravitational potentials, so to speak. So it's not qualitatively so very different from the gravitational force. In a different direction, sort of the general theory of Newtonian mechanics and its forces led to Lagrangian mechanics, which involved high-dimensional abstract configuration spaces. Then the jump to infinite-dimensional Hilbert space is also, it's sort of a continuous process. And it all started with the gravitational force. And all of this makes it a lot more difficult to relate mathematics to physics, because this mathematics is, again, it's not of a very obvious sort. But it's even more difficult. And that's because of the role of models. So it's clear from mathematical physics, or even theoretical physics, that mathematical models play a very important role. And I will say a little bit more about models later on, but for the moment you can think of them as models of theories. And theories of mathematical physics, again, you can think of as general relativity, quantum mechanics, quantum field theory, statistical mechanics in a suitable, hopefully axiomatic mathematical framework. And such theories have models. For example, a space-time, solving the Einstein equation, is a model of general relativity. Or if you describe a quantum mechanical system by a Hamiltonian on some Hilbert space, that's what I see as a model of a theory. So that you could think of. And then, so we are here in the Mecca of philosophy of science, and philosophy of science includes the study of models. So here, famously, Nancy Cartwright, I think, was a professor here, one of the main philosophers of models. And in the literature on models, it's always about models and their targets. And if you look at the philosophy of science literature on models, and I just mention four very good authors here, Roman Frick, who I at least had lunch with, Mauricio Suarez, Bas van Fraas, and Catherine Elgin. If you look at these books, then typically the targets are actually very clear. So in Roman's book, it's a ship. And all of the book is about what it means to have a model of a ship. Suarez, for example, the model, this word of model is strange, but so the model is a painting and the target is the person that's painted. And with Van Fraasen, the really most sophisticated, ultra-mathematical example is that the target is the deer population in some region of Alberta in Canada, and the model is the Lotka-Volterra equation or something like that. And so in all these cases, actually the targets are completely clear, they're unambiguously given. They're unproblematic conceptually, but it's hard apparently to do computations or make predictions. So the goal of models in that case is is purely practical. But conceptually, in all these cases, the target is clear and the model is what all the philosophy is about. It's not so clear at all. But in mathematical physics, I claim, it's the opposite. The models are clear. They're difficult to find maybe, but once we have it, once we have general relativity, once we have serious mathematical quantum mechanics, and so it's clear what we're talking about. And it's the target that's actually very, very unclear. So if you look at typical targets of modeling in mathematical physics, it would be black hole. Philosophy of science literature has interesting literature on weak neutral currents. That's irreversibility, I would say, is something you would like to model. But these targets, if they are targets, are actually very theory-laden. And they are of a completely different nature from a city or a ship or the tube system or something. And so the literature on models can hardly be used. At least it's sort of off target at most, no pun intended. So that again is another reason why a philosophy of mathematical physics is more difficult than the philosophy of applied mathematics. Because typically in applied mathematics and in modeling, it's clear again what the target is, and all the difficult stuff is about the models. And in mathematical physics is the opposite. Here's an example. So this is, as you may recognize, the standard model of high energy physics. It's in fact a page from my PhD thesis, and I worked as a physicist initially. And so the target, that's really, it's simply not so clear. That this is one of the events from which the existence of the Higgs boson was inferred in 2012. But can you tell me where it is, or what the target is? All right. Okay, so I intertwined my talk with various quotes by philosophers who typically say these things that I quote in a rather different context, but they say exactly what needs to be said at this stage of the talk. So it's about something else, but she says, so this is Holly Anderson, a philosopher of science. It's exactly right what she says for me at this very point of the conversation. And it's about this, for me, it's about this lack of clarity in what the target is you're modeling in mathematical physics. So she says, so firstly she notes that students of science typically learn their trade from textbook problems whose answers are at the end of the book. This she criticizes. So she says, this presupposition, the expectation of there being a single right answer we either got or failed to get, is ill-fitting in the context where science is genuinely expanding the boundaries of human knowledge. In these cases, what can be called the liminal cases of research, there just is no equivalent to the answer at the back of the book. There's no chance to check our answers against the right one to see we are solving problems correctly. And importantly, this is more fundamental than there simply being a lack of access to the answers, determined where the answers are. It's not merely that such answers exist, but we can't get to read them. They simply don't exist. There isn't an equivalent of the instructor's manual with all the right answers in it. There will never be a point where we get to peek behind the veil of the universe and see if we got it right. There's no guarantee of a path to a guaranteed, unique solution via the recommended resources for the problems that face us. There's no designated set of tools to solve it that the chapter points us towards. And even as we progress in physics, these answers don't appear. In principle, they're simply not there. So read targets for answers. And it's spot on in my story. So now, this is what the problems are in formulating a philosophy of mathematical physics. But of course, we also have to define what we mean by mathematical physics and then philosophize about it. But if you actually look at the philosophy of mathematics, then you almost get in a circular situation, because almost every philosophy of mathematics defines mathematics. And this I would like to avoid, certainly in mathematical physics. And in order to avoid this circularity in defining something via saying what you mean by the philosophy of that something, I took my inspiration from something written by Revil Netz, sort of a classicist and historian of Greek mathematics. So what he says is, what unites a scientific community need not be a set of beliefs. Shared beliefs are much less common than shared practices, because shared beliefs require shared practices, but not vice versa. Whatever is an object of belief, whatever is verbalizable, will become visible to the practitioners. What you believe, you will sooner or later discuss, and what you discuss, you will sooner or later debate. So I would say that a philosophy of some practice is simply a study of the beliefs held by that practice, or the beliefs maybe normatively we think one should hold about that practice. And this breaks the circularity, because now to to see what we mean by the philosophy of mathematical physics, we only need to define the philosophy of mathematical physics as a practice. That will be a practice, and our beliefs about it are its philosophy, so to speak. So we come to a much easier problem, namely what this practice is, and just, although you will see that I typically take a historical approach, I just looked to the present for inspiration. There are two major journals about mathematical physics, the Journal of Mathematical Physics and Communications in Mathematical Physics. And how do they define their scope? So the first one says, the Journal of Mathematical Physics features content in all areas of mathematical physics. This is somewhat circular, so it's not enough, I think. Articles focus on areas of research that illustrate the application of mathematics to problems in physics, the development of mathematical methods suited for such applications, and the formulation of physical theories. And then CMP says, the mission of communications in mathematical physics is to offer a high forum for works which are motivated by the vision and the challenges of modern physics, and which at the same time meet the highest mathematical standards. And so combining this, and also combining sort of this with a look into the past, so my definition of the practice of mathematical physics is in blue here. So I propose mathematical physics is the study of rigorous and sophisticated mathematics, and rigor and sophistication is by contemporary standards, which means for the Greeks it was different than for Euler, and different for von Neumann, and different for us maybe. So that's important. For the study, and study is broad, you can take the explanation or the description, it's all included of inanimate nature. And given that this is a practice, actually mathematical physics, it did not start with Newton or even Galilei, if you like. It's much older. So according to this definition, mathematical physics started with what is called the mixed sciences in antiquity, so the Greeks. Especially astronomy, but also harmonics, mechanics and optics, things that the famous Euclid also wrote about, Archimedes and especially Ptolemy. I would say this is the beginning of mathematical physics. And the Almagest by Ptolemy, precursor of Copernicus, is the first serious work in mathematical physics as I see it. And so studying its structure also gives information about what I think should be the philosophy of mathematical physics, as we will see. Copernicus, Galilei, the whole stuff leading up to Newton, that's all mathematical physics. This went on in the 18th century with partial differential equations. 19th century gave statistical mechanics, classical field theory. And then GR, quantum mechanics, all of this I see as mathematical physics once written in a mathematical language typical of what was then meant to be sophisticated and rigorous. So the scope of mathematical physics is enormous, which is also what attracts me. Okay, so we've now, by all means interrupt if you disagree, but we've now defined the problem. So we have defined mathematical physics as a practice. Its philosophy should be the study of possible beliefs about that practice, hopefully arriving at a sort of prescription or good description. And I'll now explain some of my sources, or what I see as the philosophical landscape around the philosophy of mathematical physics. And this is somewhat unexpected maybe. So firstly, I take a very sort of long historical approach or arc. So I really start with even Aristotle, who actually did not believe in the possibility of mathematical physics. So he had various reasons why mathematics could not apply to physics. But his philosophy of science is crucial. Then Ptolemy, Galilei, Kepler, Newton, so did this period from antiquity to early modern science is extremely important in forming an image of mathematical physics and possibly its philosophy. And I can only recommend, so the names of the less famous people between brackets are authors of books that inspired me. So Dijksterhuis was a Dutch historian of science. He wrote many books, but the most famous one is called The Mechanization of the World Picture, still in print, and I highly recommend it as a survey of this period. Then, strangely enough, I was greatly inspired by Wittgenstein, and then both by middle, as they call it, and late Wittgenstein. So I think you all know there were three periods. Early Wittgenstein is the Tractatus. Middle Wittgenstein led entirely to unpublished works, thousands and thousands of pages. Later, published after his death in sort of a controversial way. There are lectures on the foundation of mathematics, remarks on the foundation of mathematics, none of which he prepared for publication. But the philosophy of mathematics was a key theme in his so-called middle period, which is about the early 1930s. And he developed a non-referential philosophy of mathematics, partly based on the analogy with chess, that he extensively wrote about, but he never finished this. And in late Wittgenstein, it culminated in the philosophical investigations. Even that was published posthumously, but he edited and polished it for publication himself. And that was clearly meant to be published in the way it was published. And then in the preface you'll find a comment to the effect that he originally intended to follow it with the philosophy of mathematics, but he didn't do this. And so his late philosophy, which is about language, was actually largely inspired by his middle philosophy of mathematics, as is explained by various commentators. And so for my thinking or my attempts to find the philosophy of mathematical physics, I tried to use a certain analogy between his relationship between a language game and a natural language. And I sort of replaced that by a similar relationship between a mathematical model, maybe a mathematical theory, and natural phenomena. And this I found very fruitful. Another sort of landscape is associated with the logical positivists, as it's sort of a mixture of what is called conventionalism and an attempt to rescue Kant's theory of the a priori. That has also been described by many interesting commentators. So my favorite book, in fact about philosophy altogether almost, is by Alberto Coffa. I think it's called The Semantic Tradition from Kant to Carnap and the Vienna Station, which is also very funny. It's really a masterpiece. I actually have it, I bought it, I didn't bring it on my trip here, otherwise I would have shown it. You can still buy it second, it's fantastic. Later, Michael Friedman, David Stam, a lady whose first name I forgot, Ben Menachem, and Jared Warren. These people all wrote books about this combination of conventionalism and the a priori in a new sort of neo-Kantian sense. Then there is the Euclidean program of Lakatos. So this I don't mention only because we're in the Lakatos building. In fact, it's not so greatly to the credit, I think, of Lakatos. I'll tell you what it is, but like his proofs and reputations, it's completely wrong historically, but it gives interesting ideas. And so there's one book, unfortunately only in German, by Helmut Pulte. There are books by Passot and Rick. There's a book by Marcoso and Muknai. So this is well documented, and I'll tell you what it is. And also it sort of helped shaping my thoughts. And then there's the philosophy of models, although I just told you it's almost useless, because it doesn't really apply to mathematical physics. Even then, there are lots of good ideas in that literature. Okay, so this is the landscape, and it's also the reason why it took me a long time to actually get anywhere with this topic, since once I thought I was done, I found, well, all this should also be taken into account. It's not just middle Wittgenstein, also late Wittgenstein. All of this was added in the course of time. Okay, this is all predicated, this is a small intermezzo, so a philosophy of mathematical physics in a way has nothing to do with the philosophy of physics as usually studied in the sense of the measurement problem and so on. It is much more closely related to the philosophy of mathematics and also to the philosophy of science. And so, simply autobiographically, historically, so to speak, I began with a philosophy of mathematics that I developed with an undergraduate student called Kirti Singh, which has been in the archive for years now, and it's consistently rejected by journals we sent it to. This is my experience that actually the philosophy of mathematics is mainly done by philosophers who don't like mathematicians to interfere with their business. And so this comes to a head in the figures of Hilbert and Frege. So Frege is the hero of philosophers of mathematics. Hilbert is the hero of mathematicians, and they clashed. I'll give an example of that even. And I would say Frege was completely sidelined by Hilbert and should be forgotten. That's not what the philosophers of mathematics think. Okay, so one reason, so we developed a sort of Wittgensteinian, middle Wittgensteinian philosophy of mathematics, whose main, I think, property is that it's non-referential. It's lots of things more, but this is almost a defining characteristic. And I was attracted by this for the same reason as in physics. So again, in modern physics, it's simply not clear what you are talking about, what you are referring to, or what the target is. And it's very similar to mathematics. So even for the circles and triangles of the Greeks, it's not actually clear what their perfect version is, let alone C-star algebras, Lie groups. So where are they? So I'm looking for a non-referential philosophy of math, and we sort of adapted ideas of Wittgenstein, who was not familiar with modern mathematics. And lots of what he says is sort of at odds with anything beyond calculus and elementary logic. But you can still find his idea of a language game very useful. So Wittgenstein famously talked of mathematics as a motley of language games. So motley is not a word I actually knew. It's I think the dress of a harlequin. It's sort of consists of colorful patches. And that term was used because he had a sort of flat view of all kinds of possibilities. And this doesn't do justice to actually the nature of modern math. So we propose what I call a rhododendron of language games, where a language game is a rule-governed, very importantly communal activity, so you can't have your own language game. It's done by a community, and again, if you look at the history of mathematics, this is what you see. The rules, the standards of proof, what is accepted as a theorem, what people find interesting is always determined by a community. So, and this is something Wittgenstein always stressed, not so much about mathematics, but about language. And so meaning is given by the use of words and sentences according to the rules that come from this community. And there's a sort of a Brandomian twist, or Brandom, someone else I should have mentioned maybe, sort of added to the Wittgensteinian ideas that the rules should be inferential. And so the idea of a rhododendron of language games in the sense of math is that the roots are different foundations. So one foundation of mathematics is first order logic and classical set theory. Could be another one, intuitionistic logic, and it could be God knows what, second order logic, or something yet to be invented, or something already forgotten. There are all kinds of possible foundations, and each foundation just branches out into what we call branches of mathematics, like group theory or analysis. And so this is in a very formalized sense, so this is close to what is called formalism. And so it's about axioms and definitions. The rules of mathematics seen as a language games are basically its axioms and definitions, including rules of deduction. And then the question is what the origin of these rules is. And a hardcore conventionalist would say that it doesn't matter. But in science, and also I think in almost all of mathematics, what I felt was very well captured by Wittgenstein was the aspect that the rules are empirical regularities hardened into rules. only you have to sort of broaden the idea of the empirical. So the empirical may be natural phenomena or some natural sciences. It may be some heuristic version of mathematics that already existed, but does not deserve to be called mathematics by the standards of our time. This is what Hilbert stressed, for example. So Hilbert, as you know, I think, did not regard Euclidean geometry as sufficiently rigorous. So he re-axiomatized it. But it had value. So it was some sort of a pre-mathematics that he turned into mathematics in his Foundations of Geometry in 1899. And Wittgenstein himself would stress, for example, that a practice. So Wittgenstein's examples would typically be to ask someone to compute 25 times 25. So what is it?
625?
Yeah, 625, yeah. And then he comments endlessly on the nature of what you have been doing, and if you had 675, whether that's actually wrong or not. So you would have a lot of sympathy for a wrong answer. All right. So a social practice is also included as an empirical regularity. And did you actually do the computation, or did you know the answer in memory?
I think I knew the answer in memory, but I could also do the computation. But I was relatively sure.
Okay, so, but you haven't read the philosophical investigations, because it has literally this example. Okay, and so there's this sort of ping pong game, and this is really essential, between the rules and their source, which are sort of vaguer regularities. And this is also well described by Hilbert somewhere, in which he speaks of the twofold task of mathematics. So one is to propose axioms, in his case for some field of mathematics or some field of physics. That's the hardening of empirical phenomena into rules. And the second task of mathematics is to analyze the axioms and derive their consequences. Then finally, and that's also important for my talk, is the concept of truth that I think fits most naturally in this philosophy. Is not the Wittgensteinian. Actually, I'm now in Oxford, and there you're supposed to say Wittgensteinian. So you're immediately sort of removed if you say Wittgensteinian. Wittgensteinian. So this is not the Wittgensteinian truth concept. So the Wittgensteinian truth concept is in fact that the theorems of mathematics themselves are true. And that's also the truth concept of almost every mathematician and of almost every philosopher of mathematics, whether they are referentialists or not. This doesn't really fit the mathematical sciences, I think. So what we propose and endlessly defend against Gödel's theorems and so on. So what is true? Suppose that you have a theorem called psi in a mathematical theory called T, which means T has axioms, definitions, rules of deductions, complete theory. Then it's not psi that is true, but the implication that psi can be derived from T. So it's a statement about mathematics that is true, and not a statement within mathematics. And in our view, a mathematical theorem or proposition itself simply has no truth value. And that was in fact inspired by Middle Wittgenstein, although he didn't follow up on this. If you have a position in chess, then if it's played according to the rules, you can call it a theorem. And the game leading to the position is like a proof. But you would never say that the position in chess is true. What you can say is they've played correctly. This arises from the opening positions of chess seen as axioms via the rules that we agreed about as a community. That can be true. But the position, it would be silly to say that the position in chess is true. And so mathematical theorems in this way of thinking are very similar. So this will return to in the setting of models. And now we return to what I see as the best passages in Wittgenstein to go on. From the philosophical investigations, sections 130 and 131. Actually, when I gave a talk in the Sigma Club, I also went to the Sigma Club very often. And there was one speaker, but it wasn't even Tim Maudlin, who asked the audience to rise when he read from Bell. And I think I was the only one who stayed seated. Maybe we should ask you to rise, but let's not philosophical investigations. Okay, so what does he say? Our clear and simple language games are not preliminary studies for a future regimentation of language, as it were, first approximations, ignoring friction and air resistance. Rather, the language games stand there as objects of comparison, which through similarities and dissimilarities are meant to throw light on features of our language. For we can avoid unfairness or vacuity in our assertions only by presenting the model as what it is, as an object of comparison again. So to speak, as a yardstick, not as a preconception to which reality must correspond. The dogmatism in which we fall so easily in doing philosophy, and in which he had fallen himself, as the author of the Tractatus. And so on the analogy between language games and natural language on the one hand, and mathematical models and natural phenomenon on the other, so I would propose to see mathematical models in a very similar way. They're not descriptive, they're yardsticks held against nature or against natural phenomena. And how that is done, I'll discuss later if there is time. But this is the main idea. And I'm sure there are other sources than Wittgenstein that lead to this view of models. I would have no doubt that the philosophy of models has some authors who also think about models in this way. But I certainly do, and the source was Wittgenstein. And here's again another quote that was written in a completely different context, but that I like at this very stage, by José Ferreros, who is, I think, a very good historian and philosopher of mathematics. Many scientists, in particular theoretical physicists, have a strong tendency to think that the theories are even more real than phenomena themselves. This tendency stems in the last analysis from a somewhat primitive epistemology, from a lack of acknowledgement of the subtle relations between the theories that they handle so well in practice, the models subsequently established, and the data obtained from their experimental colleagues. It's the theoretician's hubris and a form of residual Platonism, ideas being more real than appearances. Paradoxically, the outcome of a too pragmatic, hence naive orientation. The subtle equilibrium that scientists like Hertz or Maxwell managed to attain, probably thanks to their mastery of both theoretical and philosophical difficulties, both theoretical and experimental practices, and their acquaintance with conceptual and philosophical difficulties, seems to have been lost in our age of hyper-specialized scientists. All right. So now we slowly come to the thrust of the philosophy of mathematics that I propose. Namely, how does pure mathematics relate to physics, where pure mathematics is seen, as I showed, as a rhododendron of language games, which is a rather formal way of looking, formal and democratic way of looking at it. And so the proposal is that theories of mathematical physics, and again, think of general relativity, think of quantum mechanics, think of statistical mechanics. There are specific language games, so there are theories of pure mathematics that happen to be applicable to physics in a way to be explained, but as they stand, there are examples of mathematical theories like group theory or set theory. So there are very specific language games within pure mathematics based on this Wittgensteinian notion of empirical regularities hardened into rules. There are models, and here actually there's a very good paper by Michael Redhead on models from 1980, and this licenses to say in the philosophy department what mathematical physicists actually do. Namely, what he means by a model is, there are actually four possibilities. It's either an exact solution to the exact equations of the theory, or it's an exact solution to approximate equations, or it's an approximate solution to an exact equation, or it's even an approximate solution to an approximate equation in the basic theory. That's how we look at this. And so space-time seen as solutions to the Einstein equations fit into that. There are many books on exact solutions of the Einstein equations, but most used in astrophysics are sort of numerical. That all fits into this Redheadian way of looking at models. And so the models of these theories, the theories come first, are the yardsticks or objects of comparison held against nature or held against, used to measure a selected natural phenomena. And the comparison is done, and in the philosophy of models literature it was especially Mauricio Suarez, who also has an LSE past, who stressed this. But if you look at the history, and so the paper I'm about to finish on this whole subject covers the whole history from Ptolemy via Galileo to the 19th century to the present. That's what always has been done. Typically, that's what is now called surrogative inferencing. Namely, you make mathematical inferences in the model and you compare these with inferences either, well, someone would say, in the phenomena, but I think it's more precise to follow Van Fraassen here, in that we don't really work directly with natural phenomena, we work with data models extracted from the phenomena. And that's a subtle sort of shift we may go into. It's not the main point I'm making, but I think Van Fraassen here is spot on. And one reason is that for people maybe pessimistic like me, there is no mathematical structure in the universe or in nature. But there is mathematical structure in data models, which are basically very elementary mathematical constructions like tables and graphs. So if you phrase this inferential practice in that way, you do actually compare mathematics with mathematics. But the mathematics on the model side is typically very advanced, like a space-time in general relativity. And the mathematics on the data model side is basic, namely a table, for example, planetary position. But it's within mathematics that you make the comparison. Okay, then another piece of pessimism that I like is that the comparison will always fail. So having concluded this over the last 25 years, almost every day in what I do, I read that officially this is called Laudon's pessimistic meta-induction, this conclusion. And so what I had in mind always when doing this, and before, was the standard model of elementary particle physics that I gave you the formula for. So when this was introduced, which was about 10 years before I started my PhD work in the mid-70s, it was the holy grail. So all knowledge about radioactivity and atoms and light, nuclear physics, particle physics, everything except gravity was in it. It was the final description of nature. And now, 50 years later, every physicist hopes it's wrong. The goal of all experiments in high energy physics and astroparticle physics is to disprove the standard model. So this perspective has changed completely in 50 years in a way that I think actually happens all the time if you look well enough into history. Okay, so, and that's why this Wittgensteinian idea of a yardstick is much better than that of a description. So again, a model is seen as a yardstick. You compare it with something. It's never a description of something because the description will always be wrong. Whereas if you measure, you can say, all right, it's 2 meters. So my yardstick is 1 meter. So we know the situation. Okay, and so models in this philosophy are, or even theories, are not primarily referential or descriptive. You may, at the end of the day, from this inferential structure, derive a referential framework, but it's always secondary. So if you, this philosopher Brandom, half of his work is about that. But that's in language. How if you start from inferences, how you actually arrive at the end of the day as a referential framework. But that it's secondary, so it's not primarily referential, the framework, or descriptive. And that sort of fits with what I said right at the beginning. it wouldn't be easy to say what it even meant when a mathematical theory of physics is referential, because the target is unclear. It's partly defined by the theory. And so consistent with our theory of truth in pure mathematics, it's never a property of a model that is true. So if you solve the Einstein equations and you get a space-time as a mathematical construction, you can't say that the fact that there is a black hole or that the black hole has a mass is true. What is true is a claim like, in this model, there is a black hole according to the theory. And that's an implication of that side. So it's always conditional. Given the theory, there's a black hole. And it's again like having this position in chess. The position isn't true. It's not the black hole being there that it's true. It's the property that the theory has a black hole solution that is true. And the step towards empirical reality is down here. Okay. Now, here's another quote I very much like, Catherine Elgin. She has a book, but she also has a paper sort of summarizing her book. This is from the paper, I think. So modern science is one of humanity's greatest epistemic achievements. So these truth deniers like me and her, we are not sort of enemies of science. That's one reason why this quote is good. So modern science is one of humanity's greatest epistemic achievements. It constitutes a rich, variegated understanding of the natural world. Epistemology could readily accommodate its extraordinary success if that understanding were expressed in accurate representations of the phenomena. But it is not. Science couches its deliverances in models that are purposefully inaccurate, models that simplify, augment, exaggerate or distort. The point is not just that contemporary science contains idealized models that are strictly false, rather science consists of them. Models enable us to understand reality in ways that we would be unable to if we restricted ourselves to the unvarnished truth. The point is not just that the features that a model skirts can permissibly be neglected. They ought to be neglected. Too much information occludes patterns that figure in an understanding of the phenomena. The regularities a model reveals are real and informative, but many of them show up only under idealizing assumptions. Effective models are what I have called felicitous falsehoods. Not despite, but because of their inaccuracy, they afford the success that they do. And so this, I think, resonates very well with this idea that models are yardsticks rather than descriptions. Okay, so did this I will skip, I think. So did this, you could ask about it afterwards, but this is Van Frasen's motivation why we shouldn't look at phenomena but at data models as something like the targets of mathematical descriptions. It's nicer to have another quote. I have many female philosophers. I've had Ferreros and Wittgenstein were the only male ones. So Penelope Maddy, philosopher and historian of mathematics. One clear moral for our understanding of mathematics in application is that we're not in fact uncovering the underlying mathematical structures realized in the world. Rather, we are constructing abstract mathematical models and trying our best to make true assertions about the ways in which they do and do not correspond to physical facts. There are rare cases where this correspondence is something like isomorphism. We have touched on elementary arithmetic and the simple combinatorics of beginning statistical mechanics, and there are probably others, like the use of finite group theory to describe simple symmetries, but most of the time the correspondence is something more complex, and all too often it's something we simply do not yet understand. Okay, now this is the last substantial point of the philosophy. Which is the idea that, so I propose or defend the idea that the theories of mathematical physics, and again think of the great theories like general relativity, they're a priori, but not in the Kantian sense, but in the sense that, as far as I know from all the books I read, was introduced by Reichenbach. And that means only that there are meaning constitutive for the branch of science that there are theories of. Whereas the Kantian a priori has this sort of lurking in the background, but in the foreground of Kant's a priori is that so the categories in his case are both necessary and intuitive, or intuitively accessible to the mind, or in the mind. And this is not something we want, given the evolution of physics. So for Kant, Newtonian physics was true and eternally true, and his philosophy was basically about it. So the necessity or the intuitive appeal, and again, as I said, and Kant would not agree, I think, already in Newton, this lack of intuitive appeal of the mathematics is lost, let alone all the mathematical physics following Newton. So the necessity and the intuitive nature of the a priori is gone, but what remains, and not so much emphasized even by Kant, is the meaning constitutive nature of the concept in these theories. And then Michael Friedman, he died recently, I think. He was a philosopher of science who books about space-time, many books about Kant, a very interesting author. So he christened this kind of a priori, the relativized a priori, to stress that it's not eternally given, but that each new theory, like of space-time and gravity, changes the a priori. Now, if we have time, we could discuss this later, but the way the theories actually define their concepts is technical. It's called implicit definition, and that has a long history, sort of culminating in Hilbert around 1900, picked up by Moritz Schlick in the philosophy of science in the 1920s. And I would say this idea of functionalism in space-time philosophy, introduced or at least made famous by Eleanor Knox, falls into this line of development, although I heard that she herself denies this. But it's a similar style of thinking where space and time are not things already given after which we find theories. They are what they are because of the role they play in our theories. And that idea certainly is there in this functionalist approach as well, but it's much older. So in mathematics, Hilbert and such people. In philosophy science, it was Schlick and his followers. I think Schlick was the guy who was shot. Wasn't he? Yeah, it's very sad. Okay. And so the example stressed by all the logical positivists and everyone is always space-time. So space-time has one kind of meaning in general relativity, but it had a different meaning in Newtonian physics, and in Urmanian parlance, it had a different meaning in Galilean physics and in Aristotelian physics. So that's what you can have in mind. And in particular, this means that meanings change with theories. So every sufficiently radical theory change, and here we have to sort of be modest, it's not so clear what it means for a theory change to be sufficiently radical. So I worked for 20 years on the relationship between classical and quantum mechanics. And it is enormously radical sort of claim by the Copenhagen people that it was something completely new, a totally new way of thinking, and a revolution in philosophy and physics. And it's actually not so clear. And maybe also in space-time physics. So once you look in the right way, there's a lot of overlap between Newtonian space-time and relativistic space-time. So this remains to be developed, and I think it's an important task for the philosophy of science to actually say what it means to have sufficiently radical theory change that leads to new ideas about what the concepts mean. But these then would correspond to the scientific revolutions, and that was a point made by Michael Friedman. Although friends of Kuhn, writing after his death, wrote that he also thought about this in that way, and then there was nothing new in Friedman. So it's something between Friedman and Kuhn. a technical point which I very much like is that in their capacity as yardsticks or objects of comparison, that this means the same. So mathematical models are intermediate between the a priori and the a posteriori. So the a priori here is given by the theories that the model is a model of, and the posteriori is the empirical world, if you like, seen through a data model a la Van Fraassen or seen directly. And models are neither a priori nor a posteriori. They are the midwives, they interpolate. And an important point is that the concept in models, so if you say we have a space-time defined as a solution to the Einstein equations in general relativity, if you actually have a space-time with a black hole or whatever, or a Big Bang, then the meaning of the concepts in that model were already given in the theory. So a model doesn't add to the constitution of meaning. Everything was already meaningful in the theory it was a model of. And then you can talk about the model and match it with reality, if you like. And there is a Kantian relic. So if you have concepts like determinism or randomness or irreversibility or whatever your favorite object of study is in fundamental physics, these are an example of my previous comment. So they are possible properties of models, and this is, as some of you know, a very active discussion at the moment in general relativity. First of all, does it mean for the theory to be deterministic? For what does it mean for a model to be deterministic? So the outcome should be that there is a concept or a definition of determinism in GR, which has to be found yet, I think. And then, given that definition, you can check whether certain models are deterministic or not. The outcome would typically be, I hope, that if the model has a Cauchy horizon, it's not deterministic, something like that. But the point is that concepts like determinism or randomness or irreversibility, they should be defined implicitly in the theory, after which you can check whether a model has that property, and that model you can hold against reality. So in my strangely developing views, reality doesn't have any property, but the model may have it. And this is sort of like Kantian, because he also put determinism, but as necessary. He put it well, in the mind, so to speak. He would never have said that nature is deterministic or causal. It's in our way of thinking about. And there's still something like that in this philosophy. Okay. I said I was going to look in the chair.
You have 30 seconds.
Then I'll check.
And then you'll be speaking for an hour.
Yes, all right. So this we. Yeah, so it's a pity for those who came to hear about the Lakatos Euclidean model. I'll do the summary, but I need 31 seconds. Is that okay?
Yeah, that is fine.
Okay. So I hope that a satisfactory philosophy of mathematical physics is along these lines, and that means it's obtained by combining firstly a non-referential philosophy of mathematics, in which pure mathematics is, as we call it, a rhododendron of language games whose rules are inferential and whose semantics is given by roughly the meaning is use ideology of Wittgenstein as refined by various later people like Robert Brandom. Meaning is equal to use, is given by use, and the use is determined by the rules, basically. This we combine with an also non-referential philosophy of science, in which mathematical theories of physics are seen as a priori and, in the sense of being meaning, constitutive. I would also say functionalist for the concepts that are in these theories. And this meaning constitution is done via the technique of what's called implicit definitions. Models of theories interpolate between the a priori and the a posteriori, and they do that because they are objects of comparison to be held against nature. And the comparison is done via what is called surrogative inference, as made explicit in the work of Suarez, but in practice this was there since Ptolemy. And the spirit is anti-realist throughout. So the history of science, I would say, defies any reasonable realism. And models are really not more than felicitous falsehoods. But it's all we've got.